Hi, this is Dr. J. One of the most important problems in control systems is on calculating steady state error of a non-unity feedback system. In this video, we are going to look at how to calculate the steady state error. First, I will solve a simple example problem very fast, and once I solve the problem, I will explain the theory behind the solution. The problem that we are going to address is this. So given a non-unity feedback system, with g of s is 12 by s plus 2 and h of s is 2 by s plus 3. So I'm going to presume you know what g of s and h of s are, all that for the first part. We want the magnitude of the steady state error for a unit step input. Okay, so what is ESS and the magnitude of the steady state error? A quick solution is this. So we want this, and this is based on the final value theorem, limit s tends to 0, s times E of s, and this is limit s tends to 0, s times E of s is R of s by 1 plus g of s. But for Laplace transform of the error signal, R of s by 1 plus g of s is correct if the system is non-unity feedback system, but here it is not. So we need to make a modification here. We need to write the transfer function corresponding to the unity feedback system. So that would be g of s by 1 plus g of s into h of s minus 1. Just plug in the values of g of s, h of s and r of s because it's unit step input. It's 1 by s. Find this limit, we are done. So this becomes s times 1 by s, then 1 plus g of s is 12 by 2 when s tends to 0. So 1 plus 12 by 2, and h of s is when s tends to 0, this is 2 by 3 minus 1. So 2 by 3 minus 1 is minus 1 by 3, and 12 by 2 is 6. So 6 times minus 1 by 3 is minus 2. So this whole term is minus 1, and 12 by 2 is 6, and the s's cancel each other. So what we have in the numerator is just 1. This becomes minus 5, and the magnitude of ESS will be the magnitude of this, which will be 1 by 5, which will be 0.2. It's actually a very simple problem if you know what is what and how to do it. But let's now assume that you do not know what g of s is, what h of s is, what is this final value theorem, and why did I make a modification in the error signal and all that. I'll explain that in the rest of this video. So the first part is essentially, let's take error as a function of time. Okay, we want the steady state error, which means we want this at the limit t tends to infinity. Essentially, e of infinity. Okay, given error signal as a function of time, we want error at time as infinity. But we are not dealing with things in the time domain. We are dealing with all these functions in the Laplace domain. So what helps us calculate the steady state error is what is known as the final value theorem. That says, given a function of time, that function evaluated at infinity is, take the Laplace transform of the function e of t, which is E of s, multiply that by s, and take the limit s tends to 0. We'll get e of infinity. That's all the final value theorem says. And now the problem boils down to finding e of s from the given transfer functions. So let's do that. I'm going to draw the block diagram corresponding to the system that's given over here, and then let's see what the error function is. Error is ideally the input minus the output, or essentially the reference R of s minus the output that we actually get. This is supposed to be the error, and so E of s is this. We notice When we draw the block diagram for the given non-unity feedback system, okay, so we have the input reference signal R of s over here, the output Y of s here, transfer function in the forward path to be G of s, and then we have a feedback transfer function H of s. So R of s is plus and H of s is minus. Now let's say what is the signal that we get here at this summation point. That will be Y of s, H of s. This is known as the feedback signal. Okay, and what is the signal that we get here? That is R of s minus Y of s, H of s. So this is the signal we get here at this point. This is supposed to be the error. Notice when H of s is 1, okay, if this term is 1, we have R of s minus Y of s, which is E of s. But H of s is not 1, H of s is some other function. Given that what we have here is not the error, the difference between the reference and the output, we have a slightly modified version of that. Okay, so we cannot calculate E of s from this particular block diagram, from this non-unity feedback system. In fact, this signal over here is known as error of the actuating signal, EA of s. Okay, what we want is E of s. In order to do that, can you think of some ways in which we can get the error signal instead of the actuating error signal? The standard way to do that is by converting this non-unity feedback system into a unity feedback system. We can do that. I'm going to show how to do that. So the trick is very, very simple. Okay, first is we need a unity feedback system. So let's add one more feedback loop over here, because at the end of the day this is what we want. Okay, but because we added an extra loop over here, we need to compensate for it. How do we compensate for it? Add one more loop, okay, that is plus 1. So this is because of the summation point convention is always negative, we have a minus 1 here. Okay, so I added a unity feedback, that is Y of s becomes minus Y of s in the summation point. To compensate for that, I added plus Y of s, which is minus 1 times minus, okay, this inner loop. Now we have the non-unity feedback system in the outer loop. If we can somehow reduce the inner loop into one single transfer function, we'll end up with a unity feedback system. So let's do that. In fact, the transformation, the simplification is simple. If you notice, in fact, the simplification is simple for H of s and minus 1. Combination of H of s and minus 1 is just H of s minus 1 in the feedback. Okay, so that should remove this loop. And now let's also remove all this back signal from this figure to white clutter. Now can we replace this G of s and H of s minus 1 with a single transfer function? That's also possible to do. R of s and Y of s. Okay. Now what is the transfer function for this whole system? That is, so we know Y of s is essentially whatever comes here, the signal here times G of s. The signal there is R of s. Okay, so there is a plus here and there is a minus here. So that's R of s minus H of s Y of s times. So this is the signal that comes here, that times G of s is Y of s. So from this we can calculate what is Y of s by R of s. Okay, so this implies Y of s by R of s is, just take this term to this side, and then find y of s by r of s. That will be g of s by 1 plus g of s h of s. Okay, so why did we find y of s by r of s? Because if we are trying to replace this by a simpler system, that is g, a reduced transfer function of s, we have the input here r of s and the output here y of s. Okay, so g reduced transfer function for this whole system will be y of s by r of s. That will be the reduced transfer function. So that we know as g of s by 1 plus g of s h of s. So instead of this, what we here have is g of s and a h of s minus 1. So there is a h of s minus 1 term in this inner loop reduction. So I'm going to replace this with its equivalent transfer function. Okay, so I'm going to remove this loop. Remember, there is a h of s minus 1 over here. So that becomes g of s by 1 plus g of s into h of s minus 1. So this is the reduced transfer function for the inner loop. Now we notice for this signal, the feedback is unity, and the error here actually satisfies error of s is r of s minus y of s. Okay, so for this new transfer function, we have a unity feedback system and we can find E of s, which is why I wrote E of s is r of s by 1 plus the new transfer function. Okay, g of s by 1 plus g of s h of s minus 1. So at this stage, I need to answer one detail. So why did I replace E of s with this term? I'll finish this video by answering that question. I need a little more space. So let's do that over here. Let's make this loop smaller. And okay, so this is the unity feedback system over here. And let's call this whole thing G unity feedback. Okay, so I'm going to call this function GU of s. So what is E of s from this figure? You notice E of s is r of s minus y of s by definition. And from this figure, we notice y of s is essentially E of s times this transfer function. Okay, so we have the error signal E of s over here. That apply this transfer function to this error signal, we get y of s. So y of s is E of s times g of s. E of s times g of s. G of s is the g reduced unity feedback transfer function. So GU of s. From this we can find E of s to be, take this E of s to this side, take the common terms, and then we get r of s by 1 plus GU of s. Okay, so that's a reason to use E of s to be r of s by 1 plus the reduced unity feedback transfer function, which is g of s by 1 plus g of s h of s minus 1. So this is a very, very simple problem, and if you have to do it in an exam, you can do it within minutes. And the theory behind that is a combination of some definitions and some simple ideas on feedback transfer functions. So I'll end this video posing a couple of questions to you all. So is that the question said the input is a step input, right? So r of s is 1 by s. Why is that the case? What else is possible for r of s? Can the input be a ramp function? Can the input be a parabolic function? In that case, how are all these things going to change? And then also for us to be able to apply this final value theorem, are there any requirements on stability of E of s? That is, what if there are any poles over here when there is a factor of s in the denominator, especially with the h of s, and the type of the system changes? Does all these results hold good? What do you think? Let us know in the comment section, and I'll see you with another video. Until then, good luck.